Hello, everyone. Thank you for joining us for this session, Build a Multi-LLM Chat Application with Azure Container Apps. My name is Anna. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenter to answer. The session is recorded. It will be available to view on demand in 24 to 48 hours. With that, I'll turn it over to our presenter. Simon, thank you so much for joining us today.
Yeah, thank you, Anna, for having me again. Again, I am a PM on the ACA team, Azure Container Apps, and I'm just going to show you guys some cool things you can build with container apps today. Today, we will be building as Anna has already hinted at, a multi-LLM chat application. This was really kind of a hobby project almost for me as well. I wanted to kind of play with a variety of LLMs and kind of compare their output. So that was some of the reasoning behind me building this application. As you can see here, we have a kind of a screenshot. And we'll get to exercise this app here at the end as well, where we can actually choose between a set of different models. We have Phi, OpenAI, Llama 2, Mistral, all the good stuff here. And then also optionally, we can feed a URL in the form of a CSV, a web interface, or a PDF to the LLM as well. And that will be ingested automatically in real time. And then we can actually interact with the LLM. And then just for fun, we actually also have the time it takes for the LLM to do a round trip. This is only inference time. So from the moment we submit the question to the server to the moment the server comes back, and then all network traffic in between is actually not measured as part of this. Cool. With that, let's take a look at this application a little bit closer. Cool. So if we take a closer look at this application, we can see this is, as most applications on ACA, a microservice app. On the front end, we have a Python application that kind of makes the front end available. So the GUI that we saw in a screenshot earlier, it essentially then interacts with the backend API, is also written in Python. In this case, we use Fast API. This backend API is actually responsible for quite a bit of activity in this application. Number one, it ingests any PDF or CSV or website that the user provides through the front end. That gets ingested, and then actually it creates the embeddings for which again, the embeddings are, you can think of them as a fingerprint or as a really LLM native way to ingest information. And these embeddings get generated by the backend app and essentially then get fed and stored in our Quadrant Vector database, which is deployed as an ACA add-on in this case. And then also what the backend API does is it brokers any questions between our model endpoint, which in this case runs on top of a GPU workload profile, and we'll review that later. That's because the models, many of the models perform significantly better for inference if they run on GPU. And so that's why the model endpoint in this case, actually Ollama, runs on the GPU workload profile. And then if the user selects to use OpenAI as an LLM, the backend also instantiates and brokers requests to the OpenAI endpoint as well. All right, so with that said, let's quickly look at our application and how it is deployed. If we go over here, by the way, you can run this yourself as well. In this case, I've made this available as a follow-along tutorial that kind of explains this in more detail on how to stand this up, how to deploy it on ACA, and how to use this application as well. So, all right, with that, let's take a closer look at our application here. Actually, I am slightly too closely zoomed in. Let me zoom out. Hope this is still visible. So we have the quadrant database in our application. We have the front-end service or the GUI. We have the model endpoint, as I mentioned before, and then we have the backend service as well. And so I want to get started kind of with the model endpoint. In this case, I've mentioned before, we are actually running Ollama. Ollama is really convenient to stand these services or these models up. It actually provides a container you can simply deploy inside of Azure Container Apps. And then it actually makes it really convenient for you to make other models available. And I'm going to show you some of this here really quickly. Again, some zooming challenges. Don't actually know. We can actually log into this container here. And then Ollama provides a command that you can just use to invoke and kind of manage the models that you have deployed. And so, for example, we can just, in this case, we can list the models that I have deployed here. If we scroll down a little bit, you can see that we have a few models deployed here and the sizes associated with them. And then you can actually also pull down new models as well. So I'm going to clear my screen so you can actually see me type my commands. And so Ollama list, I think there is a anyway, the model inventory is available on Ollama. The GitHub page also links to it. And if we wanted to make a new model available as part of this application, we could just simply say Ollama pull, let's say, llama to maybe 70B. Warning, many of these are very large, especially the larger models with 70 billion parameters. So you need to provision, and this is explained in the tutorial as well, some external storage that can then be used to actually use to store this. Cool. So that's our model endpoint in this case. And then we also have our backend here. And that before, the backend is kind of a centralized broker. It really goes and does a lot of the ingest of the PDF. It goes and creates the embeddings for that PDF. It then interacts with the model endpoint and returns the results back to the front end. We actually have quite a bit of useful logging in here as well. So I'm going to just keep this up while we start interacting with the front end here as well. And then lastly, we have the front end, and I've already pulled this up, so we can just reload this here real quick. And then, there is, we can just start interacting with our model endpoints. So for now, just let's use OpenAI. I always like to use some questions like, this is always fun because there's, of course, no real answer. And so it's interesting to see how the models actually behave. In this case, we're using OpenAI. I have no idea how long it will take us. This is very variable as to the time of day and how much traffic in general there is on the OpenAI endpoints at the moment. Usually these finish in the order of 30 seconds, maybe 45, depending on the day. So let's see, there we go, 20. So we have an inference time of 26 seconds, and then, you can kind of see what the answers are. As one might imagine, OpenAI is the most sophisticated, so it actually says it's very difficult, who the most famous people are, and it actually on its own segments these out. So, segments them into entertainment, sport, politics, technology, and so on. And so we can actually compare that to Phi. Phi 2 is actually not an LLM. It's actually not a large language model, but it's actually a model made by Microsoft. It's a small language model because it's actually intended to be running on device. Its inference and time, as we will see here in a second, is actually pretty quick. And so it's really tuned to be at a very high quality, but at a very, very, very small scale. It actually only has, I think, 2.3 billion parameters in comparison to the larger models in the 13 or 70 billion parameters. So it's pretty impressive. So let's just see. It's the same question. This time it's Phi 2. And we just submitted this here, and as you can see, the inference time is significantly faster, even compared to OpenAI. In this case, this model inference actually ran on top of the GPU workload profile, so it's actually our own GPU we're spending. And as you can see here as well, of course, it's not the most straightforward the question to answer, but then it actually provides us an output. The output is, of course, not as refined as OpenAI in this case, but it actually is pretty good. It actually justifies, why Elon Musk, how many followers he has, and so on and so forth. So pretty good answer all in all. Phi is also excellent for any type of Q&A. So arithmetic, those kinds of things, Phi does very well. So now we can actually also go back to our backend and actually see some of this as well. You can see that, we're getting information about what the backend relies on right now, right? Which code it uses, which endpoints it uses, and then we can actually also see these responses as well as the time that it takes for these responses to be furnished by the backend as well. And just for kind of the sake of fully exercising this, let's go and say we want to go and ingest something about from the web. So here's this paper on OpenAI Sora. We can just feed that into the model in this case, and I just specify the PDF, and we'll use Phi again. Or let's switch it up. Let's go to Llama, and then I'm going to ask a question of, so this paper speaks about Sora, which is OpenAI's video model, text-to-video model, and we're going to say, hey, can you maybe summarize, what's in this paper? So what's so special about Sora? So I don't want to read this paper. I just want to go in and do this, have the LLM do this work for me. And this time, again, we're running Llama 2. It also runs on the GPU workload profile, in this case, that we be using to run these models via Ollama. And I have no idea how long this takes to ingest. There is a little bit of work to ingest, then generate the embeddings, and then basically that gets spit back. So in this case, we're pretty quick. Again, this kind of speaks for running your own model on your own GPU if you really are looking for speed advantages. And then you can see, it gives us the rundown of this, right? Again, nothing here prepped. I literally just threw this PDF in here, and it kind of summarizes, there's simulation abilities, there's a creative boost of some form, there is basically counts out all the novel and special things about Sora that essentially are unique to it. And yeah, that's kind of it. So I was going to show you really quickly that this backend runs on a workload profile that is actually, I gotta go, we got CPU, and then look at these workload profiles here. And this is where all the models run for inference. So you can see there's one application running on this workload profile, and that should be the metal endpoint, which indeed it is. And so all of the inferences that we saw that weren't OpenAI were actually being answered by our own GPU workload profile in this case. So it's a pretty neat app. happy for you guys to play with it and answer any issues you might have via the GitHub issues. I learned a lot in terms of, what the difference between the models are, what the quality of each of these models and where the strengths of these models are. Really, the trade-off also between model size and inference time was interesting for me to learn about. And I hope you play with it as well and give this a go. So thank you all for letting me show this, and I hope to chat with you soon. Bye-bye.